Welcome to Brain Vision.
So we know that energy of a photon is equal to Planck constant time frequency of the photon, and since frequency can be written as c over lambda, so we can use this expression as well to find the energy of a photon. Now, by Compton effect, we have this equation where h over mc is a constant, and that constant can also be written as lambda c, standing for the Compton wavelength. And lambda dash is the wavelength of the scattered photon, lambda is the wavelength of the original photon, lambda dash is the scattering angle, and m is the electron rest mass. Also, the momentum of a photon can be found by dividing the energy of photon with speed of light, and using these two expressions over here, we find momentum to be equal to hf over c, or h over lambda, and p equal to h over lambda. So that's a very common expression. That's the de Broglie wavelength equation. So you must be familiar with this equation before. So now let's jump over to the first part of the problem. So we will use equation 2 here. So according to equation 2, we can find lambda dash to be equal to lambda plus lambda c times 1 minus cos phi, and phi is 180 degree over here. Lambda c is 1 over, oops, lambda c is h over mc. H is Planck constant, and this is equal to 6.626 times 10 to the power minus 34 joules seconds. M is 9.1 times 10 to the power minus 31 kg. C, being the speed of light, is equal to 3 times 10 to the power 8 meter per second. And lambda is given to be 0.9 nanometer. So this is lambda in units of meters. So now we can substitute all these values over here, and that gives us lambda dash to be 9.485 times 10 to the power minus 11 meter. So now that we have lambda dash, which is energy of the scattered photon, we can find lambda dash is the wavelength of the scattered photon. So now we can use equation 1 in order to find the energy of the scattered photon. So E dash is hc over lambda dash. So we are using equation 1 over here, and again substituting the values, we get this answer to be 2.0942 times 10 to the power minus 15 joules. So that's the energy, and then P dash can be found by using equation 3. So this is equal to E dash over C, or H over lambda dash, and that comes out to be 6.986 times 10 to the power minus 24 kg meter per second. So that's the first part to the problem. So instead of finding E dash and then finding the momentum, you can directly find P dash by using the second part of the third equation. So by the de Broglie wavelength equation, so P is equal to h over lambda. So once you have lambda dash, you can directly use equation 3 in order to find P dash without doing the without finding the energy. So this process is actually not needed. You can directly use P dash equal to h over lambda dash and find this answer. Now in the second part, so we have E1 to be equal to energy of the scattered photon plus kinetic energy. So Ke will then be equal to E1 minus E dash, and E1 is energy of the original photon and E dash is energy of the scattered photon. So that I already found over here, but if you are directly going from equation 1 to equation 3, then you might need to find E dash over here as well. So this is basically Hc over lambda and E dash is Hc over lambda dash. So now you can again substitute lambda and lambda dash over here, or lambda and E dash over here if you already have E dash calculated, and solve for the kinetic energy. And doing so, you'll find this value to be 1.1296 times 10 to the power minus 16 joules. And we know that 1 electron volt is 1.602 times 10 to the power minus 19 joules. So we can divide this factor over here and find the kinetic energy in units of electron volts, and that comes out to be 705 electron volts. So the energy of the incident photon is 13.8 kilo electron volt, and therefore only 5% of its energy is transferred to the electron as the kinetic energy of the electron.